this. Okay, I'm just share my screen. Okay, so I was thinking we can first go through lenses. It's a very practical topic, so it's pretty fun to go through. Okay, so the two lenses that we are going to do is a converging lens and then a diverging lens. So let's first look at the differences, and I want to kind of write like this so we can do like a summary at the end of the day. So the first one is converging lenses. And converging lenses can also be known as convex lenses. Then we have diverging lenses. Or also known as concave. Yeah. Now, converging lenses are basically round lenses. Okay. And the symbol that we use for these lenses are like a tiny two-way arrow. Now, diverging lenses is kind of these lenses that cave in. And the symbol that we use for them is like the upside down arrow sign. I don't know. It looks like a weird stick man, but that's the sign that we use. Now, when we work with lenses, most of the questions that you're going to get, it has to do with how light passes through lenses. So if we look at lenses overall on how light passes through, if we look at a converging lens, when light passes through the converging lens, they will bend towards each other up to a point. With a diverging lens, the light rays that come in will move away from each other. Okay. So there are a few different things or a few terminology terms that we need to know. So the first one is the focal point. Now the focal point is this point, right, where all the rays meet. Now you can see in a converging lens, that's kind of easy to see. It's the point where all they meet. But if we look at a concave or a diverging lens, they go away from each other. So where do they meet? If we go to our diverging lens and we make little dotted lines back, we will see where they meet on this side. So they kind of meet on the same side where the light rays come in. Okay. Then, of course, the distance between the lens and the point where they meet, that will be my focal length or my focal distance. Again, so when we look at how light passes through different lenses, they can make two different types of images. They can make real images and then also virtual images. Now, there's a few differences between real and virtual. Now, with real images, that is images that you might think of like playing a projector, or also the images we see with our eyes actually. So with real images, the image might be enlarged, it might be smaller, but what is always true is that the image is always upside down. So a real image is an image that is formed when the light rays from an object converge and meet each other and can be projected onto a screen. Okay, so that is anything like a movie projector. If you actually go to the cinemas, the movie projector that projects the image onto the screen is actually upside down in that little room upstairs. Well, in the olden days. These days we use digital TVs, really big digital cinemas. So it's a bit different. Now, virtual images are images that is always, they are produced on the same side. We'll go through that. And they are upright. So this is, for instance, in a mirror. So if you look at yourself in a mirror, it will be a virtual image. Okay. Now, converging lenses can make both real and virtual images, but diverging lenses can only make virtual images. Yeah. So let's look at how these images are produced. So let's look at converging lenses first, and we're going to look at real images. So if we have a lens, we'll have like the normal of the lens. That is the center of the lens, if we have to imagine it. Then we'll have our focal point. And the focal point has to do with the type of lens, how much it bends, or how thick the glass is, or what the medium of the glass is made up of. Now, if we have an object that is, let's say, larger than the focal length. So if the focal length is this much or this much, and our image is further away from the lens than our focal length, then this is what's going to happen. The first thing is that we are first going to draw a line from the top of our object all the way through the center of our lens. The second thing we're going to do is we're going to draw a line that's going to go parallel with our normal, parallel with the center. And then we're going to draw a line from this point through the focal point. There where they meet, we can then draw a distance from that point all the way back to our normal. And that is going to be our image. So if this is our object, then this is our image. Now you can see with this real image, firstly, it is produced on the underside, meaning that it's upside down. You can see in what direction my arrow is showing. It's upside down. It's also larger, and it is real for that reason. Okay, now we can look at a virtual image. Now, if we look at, let me just redraw that. So with a virtual image, what happens is that we put the object closer than the focal length. So if our focal length is here, if we put our object closer, so for instance, here, so we're going to use the exact same method. The first thing that we're going to do is we're going to draw a line from the top of our object all the way down through the middle of the lens going downwards. Then we're going to draw a line from our object all the way straight to our lens. And then we're going to go towards our focal point. Now you can see they're never going to meet. Okay, So what we're going to do now is we're going to make little dotted lines from this point and this point backwards. So there where they meet. That is going to be our new image. Okay, so if this is our object, then this is our image. Now you can see in this diagram, both the object and the image are upright, so it's not inverted. Our image is enlarged, so this is a virtual image. Okay. Are you still good?
Yes, I understand.
Yeah. So let's look at diverging lenses. So with diverging lenses, they can only make virtual images. So with this one, we also have our normal. And we have our lens. Then we also have our focal point with our focal distance. Okay. Now remember, the focal point is usually, it can be on any side. So with a converging or a convex lens, the focal point is usually on the right-hand side, right? But we can also use the focal length, the distance between the lens and the focal point, and add it to the other side. With diverging lenses, the focal point is usually on this side, but by using the focal length, I can add the other one on the other side to help me do my calculations. Okay. So let's see. We're going to put our object further away than the focal point. So we're going to put it right here. And then we're going to follow our steps again. So the first thing that we're going to do is we're going to draw a line from the top of our object through the center of our lens going straight. Then we are going to draw a line straight from the top of our object all the way to our lens. Now with a diverging lens, we know that they're going to diverge into different directions. So we are going to make little dotted lines from our focal point all the way up so it meets our second one. So all the way this way. Oopsies. I just deleted that line. Sorry. All the way up. Here where they meet, we now know that it's going to go into that direction. Okay. Now, right here where they meet here, that will be my image. So you can see that they are facing the same way and they're on the same side, meaning it's a virtual image. The object here is also smaller. So we can see in the real image of the converging lens that our image was a lot larger. It was enlarged. Then in the virtual image, it was also enlarged. And then in this virtual image, it was smaller. Now, if we place our object further away from our lens in a converging lens, then our image will actually become smaller. So if I'm very close to my focal point or my focal length, but if I went to 2 focal lengths away, my image will probably be smaller than my object itself. How do you feel about the work?
I understand that.
Okay. Can I give you one question to do?
Yes.
Okay. Do you want a second to write down my notes, or or did you already write it down?
I wrote down most of it, but I didn't understand.
Okay. Perfect. Um, let's try that thing again. You know the sticky notes on the right-hand side? I'm gonna open to page 2.
Yes.
Awesomeness. You don't have to draw it exactly. I know it's going to be very difficult to draw it exactly down. So you can do it, and I don't know if you have my number. Usually I ask my students to just WhatsApp me a picture of their work. So I think in the future, if you can download the WhatsApp, it's perfectly fine. Otherwise, would be great. Do you have your phone with you now?
Yes, I do.
Do you have my number, or can I give you my number?
Can you give it to me?
Okay.
Just quickly. Um,
Here we go.
okay, yeah.
So I just wrote it down here in the corner.
Um, okay.
Awesome. So if you're done with the question, you can just send me a WhatsApp photo and then I can quickly check it.
All right. I'm a bit stuck. I've got uh, by the arrow you take it through to the no, I'm confused with this one.
Okay. So what we're going to do from the top of our object all the way through the center.
Okay.
Then from the top of our object to the center of our lens. Then dotted lines from our focal
To
point
the
to there, and then there, this one will then be our
yes.
image. Awesome. Hey, can I give you another one?
Yes, you can.
So here the object is closer than the focal point.
So you start from your focal point.
You start from your object and you want to go through the center.
Okay. Okay, I'm going to send it now. I just don't think I drew it very nicely. So
It's okay. I'm also trying my best without a ruler or anything. It's just to get an idea if you understand kind of how it works. In the exam, you have to use a ruler and be way more specific.
I don't know why, but it's not saving. I'm going to try one more time. 7, 9.
Otherwise, you can try and keep it up to the camera. Just enlarge.
Okay, I've got it.
Oh.
Just take a photo of it. Okay, I sent it.
Perfect. So in an exam, the only thing that you need to remember is to also draw the arrow of your image and then to name it image.
Okay.
Okay, that's the only thing. But the rest, perfect. Beautiful. And
All right.
so you're happy with this topic? Do you have more questions about this topic?
No, I understand it very well. Thank you.
Perfect. Okay. So I think the next topic we can do is half-life. I kind of like half-life because it's weird to do it in physics because it has more to do with chemistry than physics. And there's so
Yes.
many practical applications of it as well. I mean, we use half-life as well to date the age of fossils and all of those fun things. There was a study, I can't remember what they said. I'm going to think about it. I'll let you know. But it was also a very interesting application. Oh, they used radiation a few scientists they were basically, just chatting and thinking about weird concepts, because people don't always just think about serious concepts. And they were wondering if there was a way to prove if there was civilization, an intelligent civilization before humans, so far back in time that nature would have basically gotten rid of all evidence, meaning that we won't see any buildings, we won't see any technology, that they lived so far back in time that they're completely gone. And what they did is they thought about, okay, what if humans disappeared from Earth? And how long would it take for everything to disappear? And if everything disappeared, what would be left of us? And the one thing they came up was nuclear power and then coal power stations. And then they kind of looked at the half-life and the radiation that those elements would have still given off. And they tasted elements of the byproducts of them, and they couldn't find anything. So they concluded that there might have been life, intelligent life before us, but we don't have any proof of it, which was a sad ending. But it was kind of cool how they decided to use science to prove or disprove it. Okay, so
Yeah.
half-life is basically the time that it takes for half of the nuclei of an isotope of a sample to decay. Now, if we look at how the nuclei of any sample decays, it doesn't decay at a constant rate. It kind of does its own thing, but if we zoom out, because it takes really long to decay, we're talking about millions of years here, then it kind of gives us a graph that looks like this. Okay, so as time moves on, it starts decaying slower and slower and slower. So at the start of our time, we can see that it decays pretty quickly, and then the decay slows down and to a point where it kind of never really disappears. It kind of goes parallel. Now, when we look at this graph, there's one more thing that comes to this graph, and that is called the background radiation. Now, background radiation is radiation that's always present in an environment. Now, this is everywhere, even on outside your house, inside your house, everything is radiating something. So this is why it never really goes to zero at all. So if we test radiation of an isotope, there is always radiation around it, inside of it, because there's always other molecules that interact with it as well. We cannot really isolate it, even in a vacuum. There will always be particles everywhere else. Now, we need to take this into account, but that's easy at least. Let's talk about half-life. Okay, so if we look at our graph, we can look at the activity at time 0. So at time 0, yeah, our activity is right up here, even maybe higher, but let's say it goes parallel. So it's all here. So we can say this is at activity 0. Now, if we take activity 0, which is here, and we half it, which means I would say half is about here. So half the activity is here. So this will be A, activity at 0 divided by 2. Now, if we connect this line to our time, we can say that this is our half-life. Now, the second thing that we can do is we can take our half our activity 0 and half it again. So it would be a quarter, about here. So this would be a quarter of our original activity. And if we connect it to this line, we can kind of see a weird pattern. So this would be our quarter time. But our quarter time is double our half-life time. So if you look at this distance, it's exactly the same as this distance. So the time that it takes for the activity of the sample to decrease from 100% to about 50% is the half-life. And then this same length of time that it took to decrease from 100% to 50%, the same length of time it will take to decrease from 50% to 25%. And then also to 12.5%. So 12.5 would be here, and you'll see it will take the same. Okay, this one won't meet because my graph, but it should take the same amount of time there. So if you memorize the activity time graph, then you'll be able to explain any phenomenon that happens with half-life. Okay. So usually with this graph, we use it to check the original activity of the decay. We can also use it to work out the half-life. And yeah, that's mostly what we use it for. Yeah. So let's talk about this background radiation, this line that I drew here. Now, like I said previously, the background radiation is the radiation that's always present in the environment around us or around the isotope that we're testing. Now, whenever an experiment that's involved in radiation is carried out, some of the radiation that is detected will be background radiation. So when carrying out an experiment to measure the half-life, the presence of this background radiation must be taken into account. Otherwise, our working will be wrong. So how do we do this? So first, we start by measuring the background radiation. This is called the background count. So we do this before we start carrying out our experiment. Then when we're done with our experiment, we subtract the background count from each of our readings. And this is then called the corrected count. So the corrected count is our best estimate of the radiation that's being emitted. So if we look at our graph here, what we would have done is before our experiment, before we test our radiation, we would have tested the background radiation, the radiation that is present. We then, oopsies, that's bad. Just deleted that horribly. Okay, so we would have measured this amount of radiation in the background. We then would have carried out our experiment, and our second reading that we would have gotten for the radiation at time 0 would have been this amount. But to work out our true radiation or our corrected count, we would have taken our second reading minus our first reading, and we would have gotten the corrected count, which is then the distance that is left over. Okay. Do you want to do a question?
Okay, I'm just not very confident with it yet.
Well, the best way is to try. But before we do the question, I'm quickly going to end the Zoom and then we can both rejoin just so we don't run out of time, okay?
Okay, must use the same password and stuff.
Exactly the same password. I never change it. It's for all my clients every day, all day.
All right.
Cool. Bye-bye.
Okay.